Hi all, welcome back to Capacitor and Dielectrics part 5. It's gonna be final part for Capacitor and Dielectrics. In this part we're gonna see dielectric effect on the parallel plate capacitor. Figure shows the region between the charged plates is empty or vacuum and is about field lines from positive plates to negative plates. Everyone knows that a parallel plate capacitor consists of a pair of parallel plates of area A separated by a small distance d. If a voltage is applied to a capacitor or connected to a battery, it quickly becomes charged. Exactly in figure A, one plate acquires a negative charge, the other an equal amount of positive charge, and the full battery voltage appears across the plates of the capacitor, which is 12 volt. So the capacitance of a parallel plate capacitor C is proportional to the area of its plates and inversely proportional to the plate separation. Therefore, the capacitance of a capacitor C equals to the product of permittivity of free space epsilon naught times the area of the plate divided by the distance between the two plates. Now the question is, what is the effect of a capacitance of a capacitor when inserted any dielectric materials between two parallel plates? These are the examples of dielectric materials. Start with air, mylar, a form of polyester, followed by pepper, silicone oil, water, and Teflon, a tough synthetic resin. When we inserted any of these dielectric materials between two parallel plates, the capacitance of the capacitor C is equals to permittivity times area of the plate divided by the distance between the two plates. This permittivity is permittivity of dielectric material, which is equals to permittivity of R times permittivity of free space, where permittivity R is dielectric constant. Therefore, the permittivity dielectric constant is equals to ratio of permittivity of dielectric material and permittivity of free space. It means C naught is a capacitance of the capacitor without dielectric and C is the capacitance of the capacitor with dielectric. The ratio of equation 2 and equation 1, equation 2 over equation 1, will give you dielectric constant, which is permittivity R equals to C over C naught. From the definition of the capacitance, C equals to Q over V and C naught equals to Q over V naught, where Q is remain constant because capacitor is disconnected from battery. Since dielectric constant permittivity R is equals to ratio of C over C naught, therefore it is equals to V naught over V, where V is potential difference across capacitor with dielectric and V naught is potential difference across capacitor in vacuum. Let us try to attempt these A-level questions to strengthen up your confidence about capacitance of the capacitor with dielectric and without dielectric. A parallel plate capacitor consists of two metal plates, each of area 0.4 meter square and separated by a distance of 0.20 cm. For section A, find the capacitance of the capacitor if the space between the plate is in vacuum for Roman 1. For capacitance of the capacitor in vacuum, questions already gave the plate's area is 0.40 meter square, separated by the distance 0.20 centimeter, which is 0.20 times 10 to the power of -2 meter. Capacitance of the capacitor in vacuum is equals to epsilon naught times A dy by d. We're going to substitute all the possible values into this formula to find the capacitance of the capacitor in vacuum, which is equals to 1.77 times 10 to the power of negative 9 farad. Simple like a bubble without giving you any trouble. Followed by A Roman 2, find the capacitance of the capacitor if the space between the plate is an insulator of dielectric constant 2.3. Everyone knows that the questions already gave the dielectric constant permittivity R is 2.3 and the C naught is from section A Roman 1, which is equals to 1.77 times 10 to the power of negative 9 farad. So we have to just substitute all the possible values into this equation to get the answer for the capacitance of the capacitor if the space between the plate is an insulator of dielectric constant 2.3, which is equals to 4.07 times 10 to the power of negative 9 farad. For section B, with the insulator between the plates, the insulation breaks down when the electric field intensity exceeds 1.8 times 10 to the power of 5 volt per centimeter. What is the maximum potential difference that can be applied across the capacitor? For electric field intensity E, which is equals to V over D, V gonna be the maximum potential difference that can be applied across the capacitor. D is the distance separated between the plates for 0.20 cm. We're going to substitute all the possible values into this equation by converting volt per cm to volt per meter, which is equal to 3.6 times 10 to the power of 4 volt. Or we can put it in this way without converting any volt per cm to volt per meter, where 1 over cm and cm will cancel each other. We still manage to get the maximum potential difference, which is equal to 3.6 times 10 to the power of 4 volt. Simple like a bubble without giving you any trouble. In figure B, a dielectric is inserted between the plates. Because of the electric field between the plates, the molecules of the dielectric, whether polar or non-polar, will tend to become oriented as shown in the figure. The negative ends are attracted to the positive plate and the positive ends are attracted to the negative plate. Because of the end-to-end orientation, the left surface of the dielectric become negatively charged and the right surface become positively charged. Because of the surface charges on the dielectric, not all the electric field lines generated by the charges on the plates pass through the dielectric. Figure C shows some of the field lines end on the negative surface charges and begin again on the positive surface charges. And the dielectric constant permittivity R is the ratio of E naught and E. E naught is electric field strength of the capacitor in vacuum, whereas E is electric field strength of the capacitor with dielectric. From the relationship between E and V for uniform electric field, where D is remain constant, we can justify the permittivity R, dielectric constant, is the ratio of E naught and E. Explain briefly the effect of dielectric. When the dielectric is inserted between two parallel plates, where the circuit is connected to battery V0, the molecules of the insulator are polarized by the electric field in between the plates. Molecules are polarized in between the plates. The reverse electric field is set up. E1 is the electric field strength between two parallel plates, and E2 is a reverse electric field is set up in the dielectric. Then the resultant electric field between the plates is reduced, where E1 minus E2 for the constant D. When E decreases, V decreases as well. If the capacitor is still connected to the battery, charges continue to flow into the capacitor until potential difference across the capacitor is equals to V naught EMF of the battery. From C equals to Q over V, V remain constant, C increases and Q increases as well. On the other hand, if the capacitor is disconnected from the battery, the insertion of an insulator between the plates will increase the capacitance of the capacitor and decrease the potential difference across it, where Q will remain same on either plate. Thank you for watching this video. Thanks a lot and thank you to the Lord.